Hi everyone. In this video, we shall take a look at how we can use molecular structures to determine oxidation states. I would encourage all of you to download the worksheet that accompanies this video so that you can follow along. The link is in the description below. You would well be familiar with all the different rules we have to calculate oxidation states. However, these rules have certain limitations as shown in the following examples. Let me show you what I mean. Using the example of thiosulfate, based on our usual rules, we sum up the oxidation state. We get an equation that looks something like that. We find that the oxidation state of sulfur is +2. Well, it turns out that +2 is the average oxidation state of these two sulfur atoms. In actual fact, the two sulfur atoms in the thiosulfate ion have different oxidation states. It becomes clearer when I show you the structures later. The tetrathionate ion has the formula S4O6 2-. Using our oxidation state rules, we can come up with an equation, and we find that X equals to +2.5. You might wonder when you look at the oxidation state that is not a whole number. How can that be possible? Oxidation states change when electrons are being gained and being lost. How can we have an oxidation state with a 0.5? Does it mean that we have half an electron? Well, it turns out that again, the +2.5 is the average oxidation state of the 4 sulfur atoms in the tetrathionate ion. It turns out that the 4 sulfur atoms in there have different oxidation states from each other. Lastly, in the peroxo disulfate ion, which is S2O8 2-, using our traditional oxidation state rules, we come up with the following equation. When we solve for the oxidation state of sulfur, we get a value of +7. Looking at this, you might wonder, how is it possible to have an oxidation state of +7 when sulfur only has 6 valence electrons? Again, this becomes clearer when we look at the structures. So in instances like this, we have to make use of a different method to determine the oxidation states. This is done by looking at the structures and how the atoms bond together. Now here's the golden rule. When we have a pair of atoms bonded by a single covalent bond, the more electronegative atom is assigned an oxidation state of -1, while the less electronegative atom is assigned an oxidation state of +1. Looking at the structure of thiosulfate, let me zoom in. This means that in this covalent bond, we will assign a +1 to sulfur and a -1 to oxygen. In this covalent bond, which is a double bond, we will have a +2 and a -2. In this covalent bond, it's the same, +1 and -1. And over here, the top, these are both sulfur, so the electrons are being shared equally. We don't get a plus or minus over here. So if we add up the oxidation state for sulfur here, the oxidation state is actually +4. Therefore, in the thiosulfate ion, the two sulfur atoms have different oxidation state. The one over here has 0, and the one over here, because it's connected to the more electronegative oxygen, is assigned an oxidation state of +4. And we take the average. That's what we get when we use our usual rules to calculate, which is +2. So what do these numbers actually mean? They actually reflect the unequal distribution of the bonding electrons between two bonding atoms. Oxygen, being more electronegative than sulfur, has a stronger hold on the bonding electrons. Thus, in a covalent bond, when we assign sulfur having the positive oxidation state and oxygen having the negative oxidation state, it implies that oxygen is relatively more electron-rich compared to sulfur. Let's take a look at the tetrathionate ion. Using the same rules, between S and O, sulfur will get a +1, oxygen get a -1. This is a double bond, so sulfur gets a +2, oxygen gets a -2. The plus and minus actually reflect the unequal distribution of electrons in the covalent bond because of the difference in electronegativity. Same thing over here. For sulfur and sulfur, because they are the same element, they exert the same attraction for the shared pair of electrons, so we do not have any plus or minus over here. So summing up the oxidation states around sulfur, this sulfur atom actually has an oxidation state of +5. And the two sulfur atoms in between have an oxidation state of 0. So how did we get 2.5 just now? It's because 2.5 is the average oxidation state if we were to count 4 of them. In the peroxo disulfide ion, sulfur here, we give it +2, oxygen -2. In the same way, sulfur here +1 and oxygen -1. Okay, between sulfur and oxygen also -1 and +1 here. So if we add up all of it, we find that the oxidation state of sulfur is +6. What about the oxygen atoms? This one over here would have an oxidation state of -2 because of the additional negative charge it has. So the oxygen atoms around the molecule have an oxidation state of -2, whereas the two in between here have an oxidation state of -1 each. So a single bond between oxygen is somewhat like the bond in hydrogen peroxide, and therefore the name peroxo disulfide. Now that we understand how oxidation states are related to electronegativity, we can take a look at how we can calculate oxidation states in organic compounds. The same rule applies. The atom that is more electronegative will get the positive oxidation state. Carbon bonded to oxygen. Oxygen is more electronegative, and there are two covalent bonds, so the oxygen has an oxidation state of -2, and carbon will have an oxidation state of +4. In ethanoic acid, carbon and carbon, same element, so let's move on. Carbon and oxygen, oxygen gets the negative oxidation state. Same for this one, carbon gets a +1, oxygen gets a -1. If we sum up the oxidation states, the oxidation state of carbon is +3. So going down the table, we see how the different oxidation states changes in different functional groups. So that is why when we say ethanol can be oxidized to ethanoic acid, the oxidation state actually increases from -1 to +3. So just by looking at the structure of different organic compounds, we can compare and see whether oxidation or reduction has occurred. So I hope this video has been useful for you to understand how we derive oxidation state using a different method. And that's all we have for today. Thanks for watching.